Just using Einstein Toolkit. She's an assistant professor of astrophysics at the University of Rhode Island, and she focuses on binary black hole mergers in the numerical relativity framework. So I specifically thank Deborah because it's very early. As far as I know, it's 6:45 a.m. in there.
Yeah,
Yes.
that's true.
Thank you very much. I will let you know when you have 5 minutes left before questions, and you can start whenever you're ready.
Okay, sounds great. Hi, everybody. Yeah, so today I'm just going to kind of give a introduction over binary black hole mergers with the Einstein Toolkit, what they're used for, why we do them, what the current status is. So it'll definitely be an introductory talk for any of those of you who are more experienced, but hopefully I know there's a lot of students in the room, so hopefully it'll still be good for a lot of the newcomers. So first off, this picture in the background of this slide is a numerical relativity simulation that we performed for the gravitational wave detection GW 190521, which was a detection by LIGO of the first intermediate mass black hole simulation or binary black hole system ever found. And this was a simulation and visualization that we did for that event. Hang on, there we go. All right, so first off, just to make sure that we are all working with the same language kind of and understand the same concepts, I just wanted to get us all on the same page. So first off, today I'm going to be talking about black holes. These are the densest objects in the universe. I think most of you in this room are familiar with that, but I just wanted to establish that we will be working with Kerr black holes, which are described entirely by their mass, and a spin vector, which is a three-dimensional quantity. Now, the real question here is, why do we care about simulating binary black hole mergers? What's the purpose? What's the motivation? Well, so when any accelerating object moves through space, it creates ripples in space-time called gravitational waves. A really interesting such system, the most extreme such system that you can get, is when two black holes are orbiting each other because they're both extremely massive, extremely dense, and when they orbit each other, they're experiencing a lot of acceleration. And so they're going to produce a lot of gravitational waves. And so that's what we're about to see here is a visualization of two black holes orbiting around each other and the gravitational waves that they produce. So in this case, what we're seeing in the 2D plane is just a slice of the gravitational waves in the orbital plane as they ripple outward. And then what we're seeing along the bottom is the line of sight gravitational waves that you would see if you're standing at one location looking at this. So you see them in spiral, burst of radiation for merger, and then the exponentially decaying ring down. So as I just said, Einstein's equations tell us that any accelerating mass produces gravitational waves. Now, what these gravitational waves look like depends on the mass and spin of those black holes that I was describing earlier, as well as quantities that describe their orbit, such as the eccentricity, which measures how non-circular the orbits are. And as you change these parameters, you change the gravitational waves. So in this case on the right, I'm about to show a video of what happens if we change the mass ratio. Here where I'm defining mass ratio as m1 divided by m2. And as we increase the mass ratio, we change the shape of the gravitational waves. Now, what's really exciting is that despite the fact that these black holes are merging super far away, meaning that by the time they reach us, they're extremely tiny. Like if you were to measure the distance from, I think it's here to the nearest star, other than our sun, the wiggles in space-time that we're measuring are less than the width of a human hair. So we are measuring extremely tiny things. But there are ways of actually detecting these using gravitational wave interferometry. So here, this video is a really nice one out of the LIGO collaboration that shows how these interferometers work, such as LIGO. So it'll slow down here and we can see what's happening. So the light goes down to a beam splitter, and then it goes down two different arms, reflects off of a mirror, comes back, and then it rejoins at the beam splitter in such a way that it perfectly deconstructively interferes and you don't get any light. Now, when a gravitational wave passes through, what it does is it stretches and compresses one arm at a time, causing changes in that interference pattern, showing us light on this detector. And this lets us measure, well, not us, I'm not an experimentalist, but lets them measure extremely tiny changes in distance just by looking at the interference pattern of the light. And so this gives us an entirely new way of observing the universe, an entire new way of seeing things we weren't able to see before, specifically black holes. And we have a number of these detectors, operational and very effective. So we've got two LIGO detectors in Hanford and Livingston. We've got Geo 600 in Germany, Virgo in Italy. We've got Kagra in Japan, and we've got planned LIGO India as well. And with all of these, over the last 10 years, because 2025 is a fun year, it's 10 years since the first detection of gravitational waves. Over the last 10 years, we've observed hundreds of gravitational wave signals. This plot is just showing the different, each point is a black hole that we observed in observing run 1, 2, 3, and 4, and their sizes represent their masses. Their height represents their distance. But you can see we have a whole smattering of gravitational wave signals that we have observed. And in fact, '04 just ended last month. And so now they are already starting to prepare for the next science run, which I think should start sometime next year. So lots of exciting stuff happening there. And what's also exciting is how much detectors have improved in those 10 years. So nature gave us an interesting opportunity this year where, so GW 150914, if you can see my cursor, is down here in the bottom left. So the line along the bottom is the gravitational wave signal from the very first detection of gravitational waves. And then overlaid on top of it will be this new detection, GW 250114. So in January of this year, after 10 years of upgrades, we saw a system extremely similar to the very first gravitational wave system that we observed. Same masses, same distance, kind of uncannily similar. And because the detector has made improvements over the last 10 years, we were able to see it 3 times louder because the noise was reduced that much. And so this is a visualization of that system from numerical relativity simulation shown in 3D or kind of 2D. And then down here, you can see the overlaying of the new data of the new detection on top of that first detection. And what is striking, if I can pause it back here, is just how much the noise has been reduced. And so how much more of the signal you can really see. I mean, if you look at this inspiral orbit here, for example, it was completely dominated by noise in the old case, but now we can see it super clearly. And especially exciting is the fact that you can see the ring down of the gravitational wave much more clearly, and that's exponentially decaying, so it's really hard to capture. But we are at the point now where we're reaching really high sensitivities already, and we're going to be able to see a lot, which is very exciting. And there's even more to come. So this is just the current status of where gravitational wave detectors are right now, but there's a whole bunch of planned experiments in the coming years that will cover different types of systems as well. So this plot, I really like this graphic, but there's also a lot going on, and so sometimes it can be a little confusing. So what we're looking at along what I'm going to call the x-axis here is the timescales of the orbits increasing as you move to the right, and thus the frequency is actually decreasing as you move to the right, the frequency of the gravitational waves. So right now, LIGO, it's a ground-based experiment. Virgo, Kagra, those are ground-based experiments. And they're able to observe stellar mass black holes merging, as well as neutron stars. We have next generation ground-based detectors that are planned, such as the Einstein Telescope and Cosmic Explorer. Now, if we move to lower frequencies, we have planned detectors, specifically LISA is one that I'm very excited about. So the Laser Interferometer Space Antenna is going to be 3 satellites orbiting the sun with 2.5 million kilometer arms instead of the for Einstein telescope, the next generation ground-based detector, I want to say it's somewhere around 40 kilometer arms. And so space-based, you can go way further, of course. Now, what that does is it brings your frequency range down. And what that does is means that you're able to observe larger black holes because frequency scales inversely with the mass of the black hole. So now we'll be able to see supermassive black holes, 10 to the 6, 10 to the 8 solar masses. So entirely new different systems that we're going to be able to see. These next generation detectors, both the ground-based and the space-based, are expected to come online in the 2030s. And so there's a lot to prepare for in the coming years. Okay, so we know that binary black holes produce gravitational wave signals. We know that we can observe these gravitational wave signals. Now, how do we backtrack this? How do we characterize those gravitational wave signals that we observe? So the question is, we know that gravitational waves encode information about the sources that produce them, but how do we actually do that decoding? Well, typically what you do is you perform a bunch of simulations or compute a bunch of models or approximations of if you have a black hole of this mass and this spin merging with a black hole of this mass and this spin, what gravitational wave does it produce? You create these template banks that you then compare to your data and you find, oh, look, this one matched my data most. It must mean that the black holes are this mass and this spin. There's lots of different ways that we do this. The most straightforward of which that's nice to go learn about is matched filtering. But it's basically the idea of comparing all of your template bank against your data and seeing which one matches best. So that means that gravitational wave data analysis, especially for next generation detectors, though I'll discuss why a little more detail later, is going to require highly accurate waveform templates that cover that entire space, that entire parameter space and frequency band of possible detections. Now, how do we actually generate those? Well, you guys are here in this meeting, so spoiler alert, I think you know what the answer is going to be. But why that's the case, why we need numerical relativity for this, is that Einstein's equations are a set of nonlinear coupled partial differential equations, and there is no analytic solution for the two-body problem. Binary black holes, that's a two-body problem. We can't just solve it analytically. In some cases, you can make simplifying approximations. If your black holes are really far apart, you can use post-Newtonian theories to pretty accurately approximate your gravitational waves. If one of your black holes is a lot bigger than the other one, and you just have a small mass orbiting a big mass, you can do other approximations that make things similar. But in most of the cases that we're interested in right now, we need to solve the full Einstein's equations. If your black holes are of comparable mass and you want to actually see them merge, you have to solve Einstein's equations in full. And that's where numerical relativity comes in. So this year is also an exciting year for another reason. In addition to being the 10th anniversary of gravitational wave detections, it's the 20th anniversary of the first successful numerical relativity simulation of binary black holes. So that was a process that people had spent a long time working on developing and solving and creating simulations that were stable and could actually run all the way through merger. And then in 2005, there were breakthroughs, and we are now where we are today, able to perform these simulations. So I'm not going to harp on this because you guys have already done Introduction to Einstein Toolkit, etc. But basic idea, of course, being we decompose that four-dimensional spacetime and those four-dimensional equations into three spatial dimensions and one time dimension. This lets us formulate this as an initial value problem where we can use our constraint equations to solve for our initial data and then evolution equations to evolve through time. Now, this can take days to months of time on supercomputers, depending on your system, but it's the most accurate way that we can actually evolve these systems. So, what is the current state of numerical relativity for binary black holes? Well, there are a number of relativity codes that exist. On the right here is a screen grab from the LISA Waveform Working Group white paper that came out a couple years ago. And you can see a whole bunch, including here, you'll notice Einstein Toolkit on line 1, 2, 3, 4, 5, 6 here, as well as its children, so to speak, its various forks, derivatives over here. So we have a number of different codes with different capabilities. We're able to, I'm not going to talk about hydrodynamic stuff because this talk is explicitly about black holes, but we have a number of codes that can do hydrodynamic simulations. We can simulate black holes in Beyond GR, which I'm also not going to talk about because I think you have a talk about that tomorrow. Um, and Einstein Toolkit, of course, open source. And some of these also have public catalogs. And through all this, we're able to simulate large swaths of the binary black hole parameter space for sure. Now, specifically, here is also a shot from the Waveform Working Group white paper, which does mean this plot is slightly out of date. We need a newer version that includes some of the more recent catalogs that have been published, but is still a semi-accurate, at least qualitatively, it shows us the idea of where a parameter space is covered. It's only like 2 years old. But there are lots of catalogs of gravitational wave simulations, but only a handful really of public catalogs, more than these four currently, but still not too many. There are on order 7,000 waveforms available for us to access in these public catalogs. And let's kind of dive into a little showing where we are densely covered and where we are sparsely covered. So what this corner plot is doing is it's taking that 7-dimensional parameter space, something I didn't mention, but is a very convenient fact for binary black holes, is the fact that everything just scales with total mass. And so we don't actually have to include total mass as a parameter in our simulations. We just set the total mass to 1, and then instead of needing both masses, we can just consider the mass ratio. So this takes it down. If we're just considering circular orbits, this takes us down to 7 dimensions, 3 spins for each black hole and their mass ratio. What this plot is showing is different slices of that, or no, that's not right, different projections of that parameter space. And so, for example, if we look at this bottom left one, we're showing Q, the mass ratio, versus A2 perpendicular. So A2 is the spin of the smaller black hole, and perpendicular is referring to the component of that spin that is perpendicular to the orbital angular momentum. So we often refer to that as precessing or in-plane spin, versus this one right here, A2Z, that is the component of the spin aligned with the orbital angular momentum. And then same thing for larger black hole, it's perpendicular component and it's aligned component. And what you'll notice is above mass ratio 4, there's kind of a wall and the simulations drop off. There are some more out there for sure, and that is improving and increasing, but there's still not a lot. And what you also notice is while there are some for the aligned spin cases, there are very, very few for the precessing spins out at these mass ratios. And so that's an area where we have a large gap. And then even within these other dimensions, which is more projections showing like A1 perpendicular versus A2 perpendicular, you can see there's parts where it's densely populated and some other parts where it's sparse, and we're definitely missing some data points. But the most obvious thing here, and the most striking, is that above mass ratio 4, things drop off very quickly. And that's because there are some challenging regions of parameter space that are hard to simulate and inefficient to simulate. So, what are these challenges? What are the challenges that numerical relativity is currently facing? Well, highly unequal mass ratios. Here I'm a little more generous and I say most simulations have mass ratio less than or equal to 8. That is true. I think The fall off happens even earlier than that, though, and I would say that most have mass ratio less than or equal to 4. Now, there are a handful of simulations that go up to mass ratio 128 or even 1024 using Einstein Toolkit codes, actually, out of the RIT group. But there's only a handful because it's very challenging. It requires really high resolution because you need to resolve the tiny little black hole there. And it requires appropriate gauge choices. So that's not something I'm going to go into a lot today, but the idea basically being when you take your four-dimensional space-time and you break it into three spatial dimensions and one time dimension, you have freedom in how you do that slicing. And that's what we call gauge freedom. And your gauge choice is how you go about doing that. And that choosing appropriate gauges is actually what led to the breakthrough of being able to simulate stable binary black hole simulations. And similarly, a lot of these challenges, it's a matter of finding clever gauge choices that make your simulation more stable and efficient. Similarly, highly spinning systems. So most of our simulations have spins up to zero point 0.9. I'd say most are even only up to zero point 0.8. Near maximal spins are challenging. So running 0.99, et cetera, is very hard. It also requires really high resolution. And it's also difficult to construct the initial data accurately. And once again, requires finely tuning your gauge choices in order to make this work. This is a thing that is people have solved, but it's definitely challenging, more challenging simulations to perform. And there's unrelating exactly to highly spinning systems, but just talking about spinning systems in general, precession increases your parameter space significantly. So if you're considering just aligned spin black holes, you can just parameterize that parameter space with three dimensions, your mass ratio, your spin magnitude of one, and your spin magnitude of the second. But now once you consider precessing, and each one is a three-dimensional parameter, now you have that full seven-dimensional parameter space. And so it's just really hard to fill in. And so that is also a challenge that we are facing. Similarly, eccentricity. So up till this point, I've been mostly talking about when your black holes are orbiting roughly circularly and what we call quasi-circularly because they're decaying and getting closer. Now, if your black holes are getting closer and further apart, we call that an eccentric orbit. Now, part of the annoyance here is just semantic in that there is no unique definition of eccentricity in general relativity. The definitions that we tend to use is a Newtonian quantity. Um, and so there's been some challenges within the community, both the NR community and the waveform modeling community, of coming up with a definition of eccentricity that everybody can agree on, everybody can compute. This has made a lot of progress. I do think people are kind of converging on some definitions. One of the things is whether you compute your eccentricity from your trajectories or whether you compute it from the gravitational wave themselves. That comment on gauge choices and gauge freedom, there's the benefit that the gravitational waves themselves are gauge independent. And so most people want to compute the eccentricity from the gravitational wave rather than the coordinate positions of the black holes. But that's a challenge, but it's a thing that people are honing in on. And then there's the fact that increasing eccentricity while maintaining several orbits can lead to really increased cost. So if you're doing moderate eccentricities, it's not bad. But if you want to do systems that are really eccentric, they come in, they're going very fast, but then out here they're moving very slowly. And you're having to figure out how best to uh, put down your mesh refinement as well to capture this whole very close orbit as well as very far orbit. So it just leads to some kind of computationally tricky bits to create a effective, accurate, but efficient simulation when you've got such varying time scales in one simulation. And it also adds two dimensions to the parameter space. So far, I've only talked about the eccentricity as being the dimension that you're adding, which is already enough work, just adding one dimension to the parameter space. But you also have to define where in the eccentric orbit you are. So you've got like your location in the orbit, but at that point, are you at apoapsis? Are you at periapsis? Like, where are you? And that's a quantity we call the mean anomaly, and that adds another dimension. And so this parameter space is just very challenging to fill in. And then there's also questions of length. And so, I've already mentioned how binary black hole simulations take days, weeks, months even to run, depending on the system, because they're very computationally expensive. And additionally, while we don't make any physics approximations in the binary black hole case, we are discretizing onto a grid, and that introduces errors. There is numerical error in our simulations, and those accumulate throughout the duration of our simulation. So, in addition to it just being computationally expensive to run really long simulations, um, it's also going to get less and less accurate the longer we run. And this plot on the right is kind of motivating why we need long simulations. And if we look at LISA, for example, depending on the mass of our system, it might be, so if we look at this 10 to the 7, it's in band for maybe a month. If we look at this 10 to the 6th, it's in band for several months, possibly years. And then this 10 to the 5 solar masses is, yeah, in band for at least a year. Now, these do have much smaller frequencies, and so being in band in Lisa for a year is not the same as being in band for LIGO for a year. But even so, these are still, we're going to see a lot of cycles, a lot of inspiral cycles, and a numerical relativity simulation will not cover all of that. It might reach to here, for example. And if we tried to simulate all of that with current codes, well, it wouldn't be possible. It would take ridiculously long, like completely impossibly long, and those truncation errors would accumulate. Now, you guys have talks in your schedule on Carpet X and the kind of next generation mesh refinement for Einstein Toolkit, so I'm not going to go into it at all, but I'm just going to comment that those improvements, making more accurate and efficient mesh refinements and codes, will help with this problem significantly for sure. I don't think we'll ever reach the point where we're using numerical relativity to simulate this entire system. I think hybridization is going to be the answer here, and that is what people are already do. Is earlier I mentioned when your black holes are very far apart, post-Newtonian methods are plenty accurate for simulating them. Self-force methods, the one where you have a small black hole orbiting a big black hole, those are actually pretty good for inspiral as well, even for comparable masses. And so people hybridize with those. So stitching together your numerical relativity simulation, merger and ring down with your inspiral from one of these other methods, and you can create a very long, accurate waveform. There's still some challenges to be done here in figuring out exactly where to do that hybridization. I still kind of want to make sure that we hone in on understanding how far we should be pushing our inspiral before those errors dominate over the post-Newtonian errors. So there's definitely still some challenges and some work to be done there as we prepare for these next generation detectors. And then, of course, there's the issue of accuracy. So these next generation detectors are going to see, so even the loudest signal that we just saw this year was signal to noise ratio of 80. Next generation detectors can have signal to noise ratios in the thousands. That's, orders of magnitude higher signal to noise ratios. And I mentioned that we do have discretization error because we have finite grid resolution. And while that doesn't seem to matter much yet for current detectors, it will matter for next generation detectors. And so this plot here is just showing what grid resolution we would need for different systems as we increase signal to noise ratio. And so for this horizontal line, when I published this paper, was the highest resolution in the Maya catalog. That's no longer accurate, so this line's definitely higher, but it still shows you what's like a reasonable normal simulation to perform. And you can see that for mass ratio 1, viewed face on, that's what this inclination is showing here, even at SNRs of 3,000, our resolutions are plenty sufficient. Now, when we look at a mass ratio 6 face on, as we start to reach 1,000, we're starting to need to push to some really high resolutions to be accurate. And if we add inclination, so where you're not observing the binary face on, but now you're looking slightly inclined, this gets even worse for a number of reasons, most notably resolving higher modes, which I don't think I have time to talk about. But the point is, it gets challenging for these systems, and we're going to need higher resolutions. Fortunately, CarpetX will also help with that. And then we also have issues with finite domain. And so we perform our simulations on finite grids, and then we evolve them out to infinity, and that introduces errors. If I have time, I'll mention some of the ways we handle that, but that does still introduce errors. And, I mentioned that we can reach signal to noise ratios of like 3,000 with next generation detectors. That's what this plot is showing here. So as a function of distance and mass, the colors are what SNR we might expect. And so you can see for some systems, we could even pass 3,000. And the problem is you need to consider these errors kind of on three different fronts. You need to consider how it could bias how our numerical relativity errors could bias parameter estimation, how it could potentially hide or imitate beyond GR effects, as well as for these next generation detectors, we might see lots of detections at once. And so you could also contaminate quieter signals if you mismodel the one that you're looking at. And so over here on the right, we're seeing a plot from Awesome John, a graduate student at UT Austin, showing with different numerical relativity resolutions injected and done parameter estimation on, you can see that the parameter estimation actually does recover different values from uh, the different resolutions. And so if we just look at these 1D posteriors, because I think that's easier, you can see, for example, if you were trying to recover the mass ratio here, you're going to get different values depending on the resolution that you used. And that could potentially affect our understanding of the systems that we see. Similarly, it could leave residuals in the data. And so what we're showing here is also a plot from the Waveform Working Group white paper, but showing a high resolution numerical relativity waveform in black. And let's just focus on in blue, a low resolution numerical relativity waveform, and then the residual that's left behind. And this is compared to the Leeson noise curve. And you can roughly say that if something is above the noise curve, then it is detectable, it is observable, it's affecting what you see. And so you can see that definitely at an SNR of 1,000, this is very much affecting things. And then over here on the right, we have a more simple system. We're observing it face on, but we still have the high resolution in black, the low resolution in blue, and a more moderate SNR of only 200. But you still see that resolution residual stands above the noise curve here and could be affecting things, even at the just normal standard simulations or gravitational wave observations that we expect to see. So now to shift a little bit, another challenge in our parameters or in simulating binary black holes is just efficiently covering this big 7, 8, 9, if we add in eccentricity, dimensional parameter space. So here I'm just showing some work that I did in a previous paper of kind of tackling this, coming up with ways to optimally suggest simulations in the parameter space such that the new simulation will be maximally different from all the simulations that you have up until this point. And then I just did that kind of greedily 20 times. What's the next best simulation? What's the next one? What's the next one? And it reduced the gap in terms of mismatch, which is the measurement of using how different two waveforms are. It reduced that by a factor of 2 just by adding in 20 simulations. Now, the method that I used to do this was creating a neural network that would predict the mismatch between this binary black hole system of this mass ratio and spins, and this binary black hole systems of this mass ratio and spins, predict the mismatch, and then you can use that to identify what simulation you should run next. So there are ways of starting to tackle this problem, but it's definitely tricky trying to fill in this parameter space efficiently. And then on the topic of, I mentioned briefly the finite domain challenge of numerical relativity. And so this being the issue that you're performing on a finite grid, but you want your gravitational waves at infinity. And traditionally, we have usually done this by extracting our gravitational waves at a finite radius and then either doing that at multiple radii and then analytically extrapolating, or doing it at one radius and then using this perturbative extrapolation that came out of the RIT group some years back. These methods work, but the most accurate way is to actually evolve out to infinity. And you can do this with a method called Cauchy characteristic evolution, kind of shown here on the left. And so what that means is Cauchy is our normal numerical relativity simulation. And then we dump the metric data on a world tube. And then you evolve in the characteristic kind of domain here, where you perform simulations along hypersurfaces out to scry. Um, it's really just kind of another change of coordinates in some sense, but it lets you evolve all the way out to, oh, for those of you who don't know, scry means temporal and spatial infinity. So which is where we actually want it. And that's the characteristic evolution. But the result is quite accurate because you're actually evolving your simulation out. There's still uncertainty and error introduced. There's some approximations you make, but it is quite accurate. And what this plot on the right shows is that this lets us capture memory. Specifically, there are a couple different methods you can do in Einstein Toolkit. You can use pit null, which has been around for a while and is a great way of doing Cauchy characteristic evolution. It still gives you the psi4 at infinity, so you need to integrate to get strain. Or more recently, we've introduced CCE export, which dumps the metric data on that world tube so that you can then feed it into Spectres, which is a different open source numerical relativity code, but they have a CCE module as well. And if you want to learn more about that, you can see my talk from the North American ETK meeting this summer, which I think is recorded. But the benefit of using Spectre CC module is that it directly outputs the strain. And normally to get from psi4 to strain, which strain is what the gravitational waves actually look like when the detector sees them. But that requires two time integrals. And that process, since I am almost done, I do promise, that time integral does lose this memory effect. And so something that is very nice about being able to directly observe the strain is that you have this offset from zero, which is probably not the way you've usually seen gravitational waves look, but this is the way that they physically do look. And so this is a very exciting thing to actually get to have now. All right. So with that, it's been 10 years of gravitational waves from binary black hole mergers, which is extremely exciting. And it's been 20 years of successful numerical relativity simulations, specifically of binary black holes. And with next generation detectors and next generation numerical relativity codes, we know that the next 10 to 20 years promise to be even more exciting. And so let's just keep going and see what we can do. Thank you.
Thank you very much, Deborah, for this very nice talk.